It's my great pleasure to introduce our last speaker of this first block of today's session, Cristian Valqui, from Pontificia Universidad Católica de Perú, and will tell us about co-commutative Q-cycles, coalgebra structures on the dual of the truncated polynomial algebra. Thank you, Cristian.
Okay, thanks to the organizer for inviting me to give a talk in this session. This is joint work with Juan José Guchone, who is listening right now, and his brother Jorge Guchone. And it is very new. There is a archive preprint appearing, well, in 2 hours or something like that, at 12 o'clock. So it is not very abstract, it's very concrete. We have some very concrete examples, and then we see what happens. The computations are very hard, but I won't go into details. So we begin with the set theoretic type solutions of the Young-Baxter equation, or of the Braid equation, which is equivalent. And this is a generalization of the set theoretic solutions. If you have a set, then you can have a Young-Baxter equation for sets, and then generalize it for the and then induce a solution in the vector space. And if we take an coalgebra, then this is the generalization we make. So the notion of non-degenerates for set type solutions, for set theoretic solutions, is generalized to this case with this definition: a map, an endomorphism of C square, C is a coalgebra, is non-degenerate if the second entry is invertible if we fix B for each B, in the case of the set theoretic types. And for the coalgebras, this P is the inverse of this, well, kind of inverse of this map. So we have this equation. This means that it is the inverse. We compose the morphism, and we get the epsilon of B times A. And this notion is very useful in order to classify maps. We have also a double dot column, but D is for double dot in Spanish, so which is defined in this way. We are following the theories of Ramp, who makes it for set theoretic, and we carry it over to coalgebras. And now P is unique because it's the inverse, and P and D are coalgebra morphisms from C squared to C. Now, a solution of the Braid equation, I think everyone knows what this is. It's equivalent to a Young-Baxter equation. And if S is also a coalgebra endomorphism of C squared, we say this is a set theoretic type solution. Okay, this is, on the one side, we have this framework, and on the other side, we have regular Q-cycle coalgebras. So P and D are coalgebra morphisms. A regular Q-magma coalgebra over C is this structure if the following conditions are satisfied. Well, we first require the condition of the this number 1 conditions. Here is number 1. Okay, number 1 condition. This condition should be satisfied, and the other conditions also. Soon. Yeah. So here. We need this number 2 condition to be satisfied. Okay, so number 1 and number 2, and And this is a regular Kumagma coalgebra. And we want to have additional structure on these Kumagma coalgebras, which are given by these three conditions. Okay, so this is a co-cycle coalgebra if, well, here you interchange the role of B and C, and you must have equality, but note here you have the colon, and here you have the product, the double product and the product. And 1 and 3 are symmetric, interchanging double dot with dot. And the first one is symmetric in itself. The second one is symmetric in itself. So if you have these three conditions, then you say that this is a co-cycle coalgebra. And the important point is of this second framework, with a theorem, there's a bijective correspondence. On the one side, we have the bijective left non-generated set theoretic type solutions over a coalgebra, the solutions to the Braid equation. And on the other side, we have the regular co-cycle coalgebra. So our goal is to classify these structures, and we do it on the side of the regular co-cycle coalgebras. And then we obtain the classification for the solutions. This correspondence is explained in detail in our work, which is in archive. This is from last year, I think, 2020. Also with the brothers Guccione. And now what I'm doing here, we are searching for examples over fixed coalgebras. Our goal is to classify the regular co-cycle coalgebra structures on the dual of the truncated polynomial algebra. So in view of the equivalence, it's the same as to classify the non-degenerate set theoretic type solutions of the Braid equation on this coalgebra. So we work on it, and we have, well, this is the coalgebra we are dealing with. We have the truncated polynomial algebra, which has a basis 1, j squared, j n minus 1. We have the dual basis, and then the delta, the co-multiplication is given by this formula, that of xi is this sum, or xj, xk, such that j plus k is I. And we have the co-unit given by is 0 on all the basis vector except x0, and there it is equal to 1. So as usual, we write this the morphism we need. P is from c squared to c. So it is given by these coefficients p, k, y, j, and d is given by the sum with the same indices on the coefficients d, k, I, y, I, a. So in order to classify this, the solutions, or in this case the co-cycle coalgebras, we have two steps. First, we require it to be a regular magma coalgebra. This step is straightforward. It's not that easy, but you just write down what you need, and some computation gives you what you need. And the second step is use the three equalities we just saw, which defines the co-cycle coalgebras. So that's what we have done. The first step is, as I said, it's a direct computation. The maps P and D are coalgebra morphisms, even only if, well, P0 yj and D0 yj are delta 0 a plus j. So it's only different from 0 if you have the indices I and y equal to 0. And the second one is the compatibility with the co-multiplication for P and the compatibility for D. Okay, so this is the condition, and the condition that this is a regular Kumagma coalgebra, so it's left non-degenerate on the side of the solutions, if P110 is different from 0, the same for D, and P101 is 0. So if you have these conditions, then you have a regular magma coalgebra. So that was the easy part. Now, as everyone knows, who once tried to classify a solution of the Young-Baxter equation, there are heavy computations, equations of degree 3, and well, we cannot escape from this computation. In this case, these 3 equations are translated into these 3 equations for the coefficients. So it doesn't look very nice. And actually, this is already a simplification of the original equations one obtains. But, well, we took these equations and we tried some particular cases, and then we obtain this classification table. Okay, if you have this coalgebra, then, well, it's a partial classification, it's not the whole classification. First, it depends on the coefficient P111. If it's different from 0, then everything goes smoothly. In this case, automatically P and D are equal. P1J0 is delta 1J, and you have something that we call a standard cycle coalgebra. Okay, I will explain, we'll go into detail with this standard coalgebra. It's the interesting objects that arises in this classification. I mean, the classification, I don't know how important it is, but this family we obtain is very, very nice. So if P111 is equal to 0, and if we require P equal to D, we require this condition on P1J0, and we require that one of these P11J is different from 0, then we also obtain this standard cycle coalgebras. So CC means it's a complete classification in this case. Okay, we get complete classification only in these 2 cases, and if the P110 is not a root of unity, then we also obtain a complete classification. The other cases, well, in this table they look small, but actually there are more cases that are not classified than the classified ones. But in the table it looks good, so this is the case. So I will go into detail with the standard cycle coalgebras. And so one remark, if P is equal to T, these 2 maps are equal, then the solution, the set theoretic type solution that we associated to this regular magma is coalgebra is involutive. And well, as everyone knows who works in this field, the involutive solutions are very special and are the most studied. So P equal to D is an important condition. And in this case, we call it simply a cycle coalgebra, not a co-cycle coalgebra. Co-cycle refers to non-commutative, something like that. So now we have the following theorem that I just explained in the table. If P11 is different from 0, then the solution is involutive. Automatically, D is equal to P. And the P1J0 is automatically delta. This is the delta of Kronecker, J1, rho J. And P depends only on the 3 parameters P11K. So this is a very important result, because you get a family, an infinite family of these solutions, and you have 3 parameters, and everything goes very smoothly. And if P11 is equal to 0, then you take the first element of P11I that you want to be different from 0. So this is this element. And the others, P11I is 0 for I lower than V0. Okay? And P11 is equal to 1. So you choose these coefficients. Then you also get the same results. You have three parameters, P11K, K from V0 to N-1, and this determines the whole structure you are studying. So this is our main result. And So I will give an idea of the proof because the proof is very, they are very hard computations. So I will give only some ideas. So the parameters we will have, I grouped them in a polynomial. F is the polynomial, and here are the parameters. You know, here P11V is equal to PV. This will be the free parameters. So the cycle coalgebra with these parameters is called the standard cycle coalgebra associated with F, with this polynomial. And we write SCC of F for the algebra, for the coalgebra. Sorry, for this cycle coalgebra. If it's different from 0, then pardon, excuse me. If PV0 is not equal to 1, then there is an equivalence of co-cycle coalgebras, just multiplying by a parameter lambda, and then the cycle coalgebras of theorem 7 or proposition 8, this with this free parameters, equivalent to a standard cocycle coalgebra. So we call them standard if the first condition, first coefficient is equal to 1. In the case of the proposition, we also need that this root is in K. So if K is algebraically closed, this is automatically fulfilled. So now, given F, we will define the structure in various steps. First, we set P0 UV equal to 0, except when U and V are equal to 0 themselves. Then we define another, well, we consider F as a formal power series in X. Although it's a polynomial, we consider this as a power series. So all the computations are done in power series. So we define a new power series with this formula. And then we define a power series in two variables. Well, in setting this, so the coefficients of G uppercase, if we see G as a power series in J, are functions of X, are power series in X, in degree 0 with just X. And then we have this equation, and this equation defines G uppercase. Okay, this is the step 3. So we have a power series in two variables. And then we define the coefficients P1 UV as the coefficients of G. Okay, so we have the coefficients P1 UV. And in the 5th step, last step, we define, well, recursively PW UV. This is just using the coalgebra structure of P. So it is enough to define the first coefficients. Then automatically this must be satisfied if it is a coalgebra morphism. Now this equation, this equality, is equivalent to, one can see that is equivalent to this equation, and so this is actually a recursive definition of the G V plus 1, because all the terms that appear on the right side are GV or GL with L lower than V plus 1. So this is actually a recursive definition. So now we define differential operators. We define them implicitly. Okay, so for H power series in X, we define the partial V with respect to X of H by requiring it to be the coefficient in this power series of G. H of G is well defined because G begins with X, and so well, G has conditions, so this is defined, a well-defined power series. And then we have an operator from K, from its power series in X into itself, and we can extend it just regarding the power series in two variables as power series in J with coefficients in the power series in X. So, and we act only on the coefficients. Then we can construct operators on the power series in J, just replacing the power series in J with X. So this is well known, X and J. So we start with G of J, a power series in J. We substitute J by X, get G of X, and we apply partial Vx with a series H of X in K of X, and we substitute back J into X. Okay, so we obtain operators K of J, and we extend them also to the power series in two variables. Okay, so we have two families of operators, differential operators. Actually, for V equal to 1, it is a derivation. And then we define the operator, the global operators, partial K, simply the sum of the partial A with respect to X and partial B, J. So, and why we define these complicated operators? Because we have the following equivalence. Assume that we have defined this power series uppercase G using this process that I showed, and which satisfies this equality for the coproduct is coherent with the coproduct co-multiplication, and then you have this. Well, since P is equal to D, the three equalities we saw, which were very complicated, are actually only one, because you replace P by D and the three D by P, and then the three equalities are the same. And so you have in all the places where you had D, now you have P, and with 3 times the same equation, so there's only one equation you have to consider. And this equation is satisfied. We know this is satisfied if we have a Q-cycle coalgebra. This was the hard part. And now it is equivalent to this compatibility condition for the differential operator that we just defined. So this looks very nice. A complicated equation, and now we have a very simple equation. And the equality just says you can interchange K with J. So actually here is in order to prove actually this equality, this is a very, very hard problem. So without escape from the computations. Okay, it's very nice, it looks very nicely, but it's not easy to compute. So we have to invert the composition of power series into variables and some other tools. So, but now, once we obtain this equality, we were able to compute this equality. Then we have the result that theorem 7 and proposition 8. Once we have this equality, then we have conclude the proof of this both results. So let's see some examples. For example, if we take, remember F was codifying the coefficients. So one simple case is when F is 1 over 1 minus X. Okay, so all coefficients are equal to 1. Then one can compute the coefficients, which are these combinatorial numbers. Okay, this is a very concrete example which works for every n. Note F is a power series, and we only need the first n minus 1 coefficients in order to define the Q-magma coalgebra. So this is one standard example. This is a second example, and this case actually was very, very hard to prove. We didn't have the general result, and we started with this result, which is somehow very simple. F of the first coefficient are just 1 and 1, and all the others are 0. But it took about 3 weeks or so of hard computations through the force in combinatorics in order to prove that this this definition is okay and that it gives a Cumac macro algebra. So, well, Juan Jose can testify that this was a very hard problem. But now we have the general result, and so this is just a consequence of this general result. So this were our computation, this concrete case, and now I leave you with two questions. So when we tried this standard cycle coalgebras, we had to work with a power series in two variables. Okay, so there's some dictionary that this represents a two-dimensional space, and the origins of the Young-Baxter equation are associated with two-dimensional space-time models. So is there a connection? So I looked a bit into it, but maybe there is a connection. So it would be nice, because if there is a connection, then one can see a long-term project. This Young-Baxter equation, then we can generalize it to higher dimensions, okay, using this compatibility condition for differential operators and three or more variables. So if there is a connection, then maybe there's a connection to some space-time models of more dimension, would be very nice. So there are two papers associated to this talk. The first one is, I told you, in 2 hours or so at 12:00 archive will announce the number, so it has no number. And the other one is from the last year, where the theory is explained. And thank you.